Alright folks, well this is it. I wanted to go through a bit of a wrap-up of all of the different things that we went through this term. We covered a lot of ground. This might take a little while. You might want to grab yourself a coffee or something and kick back for a bit, and we'll see how we go here. All right. Again, we started off by talking about several of the different language paradigms that we're interested in, the sort of functional, imperative, the OO side. And for pretty much all of them, we looked at the idea of pure versions of the paradigm versus the hybrid languages, and the fact that most of the languages that we use in practice are hybrids of different paradigms, just because of the benefits that it gives the programmer in using the language. And again, some of the advantages and drawbacks of the different paradigms and the purity or lack thereof. So then we went through and looked at a lot of different language features and capabilities. We spent a lot of time looking at Lisp in particular to get an idea of the feature set provided in a completely different language, and that kind of gave us the ability to do a bit of a better compare and contrast with sort of the extremes of a Lispy approach versus a C approach. So we did look at some of the implementation ideas and considerations with different features in the languages, right? What are the implications of how you handle let's say the implementation of dynamic scoping, or how you handle the implementation of lists. So a lot of these things we touched on at different points. I want to try and give a bit of a summary for a lot of it as we run through this today. And again, the idea is that if we've got an idea of how different features are implemented, that gives us a good understanding of how we can use them effectively, or what kind of uses will be ineffective or inefficient. Right? It gives us the ability to take advantage of the benefits and avoid some of the worst traps associated with different features and implementations of them. And it also gives us the ability to implement a feature of our own if a language doesn't naturally support it. Right? If I know how some feature is implemented in my favorite language, then I know that in another language, if I'm working in C or something like that, and I want that feature and the language doesn't provide it, I can come up with a way to provide myself with that functionality, and I'm aware of the different techniques I can use to provide the functionality, and again, the advantages and pitfalls of the different implementation approaches. And again, from my own perspective, it's just plain interesting to see how some of this stuff is done, how things work, right? How some of these high-level abstractions can be made to work at the very practical, low assembly language level, right? If you've only got these primitive operations, how do you build them into something that gives you the advanced functionality that you want? Now, in this field, things change all the time. If you're going to stay relevant in this field for the next 20, 30, 40 years, however long you plan on doing this, then you're constantly going to be learning new languages, new features, and entirely possibly new paradigms as time goes on. If you're curious about how this stuff works, it makes your life in this field more interesting, right? If you've got that active curiosity, it is much more rewarding to be able to say, oh, that's how it works. Treat things like a puzzle, be willing to experiment, be willing to explore language features, be willing to dig under the hood and find out how things work. And that will keep you both interested and effective for a lot longer than otherwise. Anyway, that's my soapbox. What I want to do is, again, run through kind of a timeline of what we looked at over the course of the last few months. So, way back when, we started with a look at Lisp, right? Getting basic fluency with the language, dealing with the idea of dynamic typing and type checking, and all of the different pitfalls that come along with that, looking at the different data type hierarchy that Lisp provides, right? This notion that we've got sequences as our general kind of collective type, and then lists fall under that, and arrays and vectors and strings and things fall under their own little hierarchy under sequences. We looked at the way that lists are actually implemented and some of the implications for that in terms of side effects inside functions, right? The joys of setfs and things on cars and cutters of lists. We looked at the different layers of equality testing that Lisp provides, right? The EQ versus equal P versus EQL, right? All these different ideas that provide you with different functionality. Right? We looked at the idea of lexical scoping versus dynamic scoping, right? Let blocks versus declaring something as special versus what defvar does and what happens with a setf. So again, all of these things are things that hopefully come flooding back as we get ready for finals. We looked at recursion and the idea of using accumulators and tail recursion to try and provide a recursive technique that can be optimized so that we're not constantly reusing new stack space, and so that the compiler, if it recognizes it, can provide us with a much more efficient executable than we would normally associate with recursion. We looked at some of the different parameter passing mechanisms, so looking at things like optional parameters and default values, and keyword-based parameter passing versus positional. We looked at variadic parameter passing in Lisp using and rest. We looked at hash tables and structures and symbols and property lists and all the joys that come along with those. Right? The idea of a symbol, of a name being something unique in and of itself, something that we can actually manipulate and bind to values or variables and unbind as time goes on. We looked at a variety of different higher order functions, right? Fun call and apply and eval and map card and map list and all that sort of idea. We looked at creating our own anonymous functions, lambda functions, the use of let over lambda to get a sort of OO-like quality to things, and why that actually works behind the scenes because of the implementation of lists again. We looked at incorporating labels into that, so you've got your let block over you've got your let block over a labels block over a lambda, right? And the idea of using this lambda function as kind of a dispatcher to issue commands to interact with this hidden stored data someplace. We looked at the idea of homoiconic languages in general, right? Languages that can read themselves as data, and looking at macros and having macros rewrite the language for us to provide us with new functionality. We looked at the idea of parsing Lisp in Lisp, right? Using this kind of homoiconic idea to go through and say, okay, well, maybe I can have my Lisp code read portions of itself and form new Lisp and use that, or form new code as it goes, and use that as it executes. And we got into a little bit of the pure versus hybrid aspects of Lisp, and looking at ways that we could take different existing features and create pure versions of them, possibly rewrite them using macros to create those pure versions without the developer's awareness, but some of the pitfalls that come along with that as well. We looked at some of the underlying C implementation of Lisp and some of the implications of that, and how some of that explains the behavior that we see from Lisp. And then a whole collection of miscellaneous bits and pieces, right? Pipes and file I/O and packages and compilation and that kind of thing. Then we got into the sort of formal description of languages, so the use of formal grammars, and this kind of tiered approach where we've got regular expressions for the tokens, context-free grammars for the basic syntax parsing, and then augmented grammars to get the context-sensitive rules and meanings into place. We looked at some of the automation of this process, right? Things like Lex for doing the tokenizing for us, things like Yak for doing the basic parsing for us, and then the expansion of our Yak rules, right? The addition of these C segments so that we could augment what Yak is doing and saying, okay, as you parse it, if you recognize one of these things, do this with it, or analyze it using this. Now, I am going to be assuming that you've got kind of basic fluency in Lex and Yak, but nothing too extraordinary as far as the final goes. Again, continuing on with the sort of parsing side of things, we spent a bit of time looking at context-free grammars in general, the idea of tokens and non-terminals, derivations where you're starting from some generic starting non-terminal and you're trying to derive a particular sequence of tokens in the language to see if that token sequence is actually in the language or not. the idea of the sort of step-by-step derivation process, leftmost versus rightmost derivations, and then kind of relating that to the idea of our parse trees and having this sort of this tree whose root is our start non-terminal, and it devolves down into eventually the leaves at the very bottom of the tree, which are the tokens. And if you go through and do kind of an in-order traversal of your tree, you wind up seeing the tokens in the order that hopefully they appear in the code that you're trying to parse. Again, we took a look at the relationship between having multiple different parse trees for a token sequence and the fact that that means that the grammar is ambiguous. A little bit in terms of what the tree shows us in terms of order of evaluation, right? When we're going through and actually evaluating the token sequence, we tend to do a bottom-up approach to the evaluation, so that let's say operators that appear higher up in our parse tree are evaluated later, which means they have effectively lower precedence as far as the language is concerned, right? As far as our grammar is concerned. So again, the notion of how associativity and precedence is revealed in our parse trees. We got into discussing language features, and as sort of a prelude to that, we got into the idea of attributes and binding in a language. So looking at the idea of static binding, features that are determined, that are fixed at compile time, that we know simply by looking at the source code, versus dynamic binding, things that can't happen until the program is actually executing. And then within the dynamic, there is this little gray area of sort of fixed dynamic versus truly dynamic, where there are some things where you've got an attribute or a feature that isn't bound until execution, at some point during execution, but once it's bound, it's stuck forever. So it's kind of fixed after that point, versus things that are truly dynamic and can be set and changed later and changed later and changed later as the execution continues. And then a few of the features that we looked at were things like names or symbols, when are they bound, data types, when are they bound, storage for an item, when is that bound to the item, the scope and the lifetime of, let's say, a variable. What is the scope, where is it visible, the lifetime, when does it start to exist versus when does it cease to exist. And we got into discussion of types and type checking in particular, static versus dynamic typing. We've seen good examples of that now between Lisp and say a C or a C++. You've had lots of experience now in handling programmer-controlled runtime execution or runtime checking of data types. And the alternative would be to have our language, our compiler, somehow try and insert runtime checks for the data type at the point where a value is going to be used if you were using a dynamically typed language. Explicit versus implicit conversions for data. When does the programmer actually write something that says, okay, now convert this data type to this data type, versus the implicit ones where the compiler goes, oh, you're using this in this context, that means I should do a conversion to whatever the necessary data type is. And going along with that, the idea of widening versus narrowing conversions. We talked a little bit about name type compatibility versus structural type compatibility and why that's relevant, where that has meaning for the programmer. We got into the primitive types. Again, the usual collection of characters and integers and reals and booleans and ordinals, and then depending on the language there might be additional types supported, rationals and complex numbers and that kind of thing. And again, the usual idea of what kind of operations do you want to support, and what's the underlying implementation of the data type, and what are the implications of that for the programmer. So what if you've got a fixed bit size for a real number, what does that mean? How much of that's carved up for an exponent, let's say, and how much of it is carved up for the precision? What kind of representation are you using for a Boolean? Is it a single bit? Probably not. It's probably represented as whatever your smallest addressable type is. Right? So again, thinking about the implications and the implementations of the different types. Then in terms of the composite types, things get a little bit more interesting, right? What are you using as your implementation for strings or for arrays, one-dimensional arrays versus multi-dimensional, for hash tables and records and structures and unions and pointers. And again, all of the different practical implementation aspects that go along with that, for records and structures. What do we have to worry about in terms of memory alignment rules and padding or reordering things? For arrays, what do we have to worry about in terms of row major order or column major order? Right? For unions, what's the impact on type checking for the language? For pointers, oh well, we've got all the usual slew of problems with pointers in terms of memory leaks and dangling pointers and everything that goes along with that. Looking at all of the different things that we should consider for a programming language with respect to operators and operations, right? How many operands can an operator accept? Is it, 1, 2, 3? What's the associativity? What are the precedence rules for your operators? What kind of notation are you using? Infix, prefix, postfix? Do you allow operator overloading? Do you allow the definition of new kinds of operators? How are side effects handled? Again, what's the order of evaluation? Do your expressions do short-circuiting? What kind of an impact does that have? What's the implications for the programmer? If you've got parameter passing, where does the order of evaluation take place there? When do you evaluate the parameters, in what order, and how does that interact with side effects in the expressions? We looked at some of the different control features, right? The underlying sort of test and branch, ifs and go-tos, if you like, that are controlling our if statements and our selection statements and our loops. Looking at some of the possible different structures of the different loop types, the difference between maybe a while loop and a do while or a repeat until or a for loop. Looking at some of the possible structuring for switch statements. Looking at the control structures in particular when we're looking at blocks, whether it's just a standalone block or whether it's as part of a selection statement or whether it's as part of a loop. Do we have a single entry point? Do we have multiple entry points? Can we have a single exit point or multiple exit points? What are the scoping rules associated with that block? What kind of storage and initialization rules do we have with it? Does the block return some kind of a value? Right? For selection, is it single way or two way or multi-way? For iteration, again, all of the different loop styles and some of the special features that come along with that in terms of breaks and continues and lasts or finally or whatever it might be, top tested versus bottom tested. Right? Iteration across a data set instead of across a specific sequence, so something like a for each loop. All of the fun and joy that comes along with subroutine handling. Right? Do we allow nested subroutine declarations? What different parameter passing mechanisms do we support? What are the call and return sequences and mechanisms? What are the scoping rules? Do we allow overloading of subroutines? Do we allow variadic parameters or parameter lists, variadic functions? Do we allow higher order functions? What kind of support is there for that? Lexical and dynamic scoping, scoping again. Do we support generic functions or templated functions? And again, behind the scenes, what are the implementation techniques used for each of them, and what are the implications of that for the programmer that's using the language? And we got into discussion of macros and kind of comparing how they work in something like Lisp versus C versus C++. Right? The idea of a Lisp-style macro where you can really do some major rewrites on the language versus the C-style hash defines for simple text-based substitution versus the C++ template style, right? What are the implications for the programmer in terms of these rewrites? What are the implications for the poor compiler writer that's got to support the macro process? What are the implications in terms of debugging? So again, lots of different things to consider for that. Higher order functions, once again, how much is that supported in the language? The different styles that we took a look at, right? The Lisp style versus the use of function pointers in something like C, or maybe expanding that a bit with templates in C++. The Variadic functions, again, how well is that supported in the language? The Lisp style where we were playing with andrest versus the C style using the macros in stdarg versus the C++ style where we used recursive templated functions. Again, it gives you a pretty good look at a variety of very different ways for supporting this. And obviously, depending on who you are as a developer, some of these are going to feel way more natural than others. Again, getting into dynamic scopes and nested scopes, what does that look like behind the scenes, under the hood? What kind of implementation details are associated with something like that? You know, for dynamic scoping, there are a few different ways we could go through and implement that. We could either take a Lispy approach and just take all the information about the current execution environment and just pass that to the function and say, here's the definitions and stuff that exist right now, you know, do with it what you will. Or we could keep some kind of global stack so that for every individual name, we've got a stack of the current values that are available for that. Or we could go through and, using the stack frames, let the called function have some kind of a reference to the caller's stack frame and some kind of a mechanism for going through and extracting the variables they're interested in from that. Or for nested scopes, again, using a similar idea where we give, if one function is declared inside another, then we give that inner function a pointer to the outer function's stack frame so that it's got access for the variables that are declared there, for instance. And we got into discussion of some of the dynamic memory management issues, right? Management of heap space. How do we go through and keep track of the free and allocated space? What might that look like in terms of the overhead when we're going through and actually allocating these chunks of memory for a program? What kind of administrative information has to go along with that? So what have we got in the way of extra administrative information in the chunks that are allocated? How do we go through and efficiently determine what's the best free chunk of memory to provide in response to a request? If a chunk of memory is freed up, how do we put that back into our collection of free memory? You know, what can we do in terms of preventing or resolving memory leaks? What can we do for garbage collection? What can we do to deal with memory fragmentation issues? And we took a look at a kind of GNU approach for handling this. We got into a bit of discussion on smart pointers, and again, just some mechanism for trying to avoid the pitfalls associated with giving the programmer direct control over pointers in terms of news and deletes, or mallocs and frees, or whatever your syntax happens to be, right? Wild pointers and null pointers and dangling pointers and memory leaks, right? What can we do to try and provide a safe memory allocation and deallocation mechanism that avoids those problems? And again, the idea of using something that provides this sort of hidden internal pointer to where the real data is, and having a reference count for how many things are actually going through the smart pointer to get at it. And we took a look specifically at the C++ approach, most particularly with the shared pointers, but also the relevance of weak pointers and where they might come in. And then we kind of wrapped up with a little bit on abstract data types and OO handling. What sort of support does your language provide? Does it provide enforcement, right? Are abstract data types or an object-oriented approach actually enforced, or are they, again, is it kind of a hybrid approach where you're given the ability to use ADTs if you want to, or the ability to use an OO approach, but you're not actually forced to adhere to sort of strict rules around those? And again, the notion of what are the implications of the inheritance mechanism that you're using, the method dispatch mechanism that you're using, what comes along with things like multiple inheritance, how do we handle dynamic binding to methods, what are some of the different implementation possibilities? And again, we took a look at some of the C++ side of things, right? The idea of adding this pointers to your functions, renaming your functions to kind of represent the different methods associated with a class, the idea of these v-tables to go through and track the different collections of methods that were associated with classes and with objects. So again, just a bit of a feel for how things work under the hood and what the implications are for the developer. So that was about the point where we left off. Again, that's an awful lot of material. Hopefully folks found the course interesting and not too insane. We'll see where things go from here. Good luck on the final exam. I'll post a separate section talking about the exam style and questions and that kind of thing. But hopefully folks enjoyed the course. Have a good summer.